Hi students, now we are going to look at the refraction and reflection of a plane wavefront on a refracting surface and also on a reflecting surface respectively. First, we are going to see the proof for the laws of reflection using Huygens principle. First, what is meant by Huygens principle? Now, we know, before looking on to the Huygens principle, we must know what is meant by a wavefront. See, so this is a light source. Here, light waves are coming. So they vibrate in different direction. Right? So these are the vibration of light waves in different direction. Now they have a crest. That is crest, 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 crest. Trough, 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 trough. Right? So now, when I join all the crest part of these light waves, so these points on the crest are joined by a circle-like line, right? Curve. Now, this is what we call as a wavefront. Even when I join all the trough parts using a dotted lines, again I get another circle. So like this, we have some concentric circles like this. So these are called spherical wavefronts. So what is meant by wavefront? When I drop a stone on the stagnating river, so this is the stone. Now what happens? Some ripples will be formed around the stone. So it means the waves from this point where the stone has been dropped, right? The waves would have started in all directions and forms a concentric circles like that. So these rings which are looking like a concentric circle, right, they are nothing but the crest part of each wave which spread out in all direction from this point source or where the stone has been dropped, right? Now if I cut this portion and look from this direction, that is, if I look the front view of this cut portion, so I can see a portion like this. So this shows the crest part and the trough part, then the trough part here, like this. So these are the waves which spread out in all direction from this point object in different direction, forming concentric circles. So wavefront is the locus of all the particles which are in the same state of vibration. Here in this region, all the particles, water particles, they vibrate in same phase. They vibrate in same phase and form a crest. And here this region forms the trough part. And here again, a wave is formed with a greater radius than the first circle, and this is the crest part of the second wave. which has formed. So here the particles present in this second circle, they all form in phase. So like that, each concentric circle represents the particles in each circle, they will vibrate in phase. So here the locus of all the particles, focus means fixed point, locus means the movable point or moving point. So the locus of all the particles which are said to be in the same state of vibration, that is what we call as the wavefront. And Huygens principle, what is meant by Huygens principle? For example, so this is the crust part. I'm joining here. These are the points I'm marking on this spherical wavefront. This is the spherical wavefront. See, when the source is kept far away from us, this spherical wavefront becomes a wavefront called plane wavefront. So if the source is at infinite distance, the wavefront obtained is a plane wavefront, right? Now, each point on this first wavefront, according to Huygens principle, each point on this first wavefront act as a source of secondary wavelets. Wavelets means tiny waves like that. Okay, so they act as a source of, these points act as a source of the secondary wavelets, and we know that c is equal to d by t. The velocity of light, c is equal to distance by time taken. Now d is equal to c into time taken. So the velocity of light into the time taken. So keeping this distance as radius and these points as centers, I'm going to draw different wavelets, that is circles or arcs, like this. So when I envelop all these wavelets, I get a new wavefront, that is a new spherical wavefront. So Huygens principle states that each point on a wavefront acts as a source of secondary wavelets. So these secondary wavelets, after they are enveloped or covered, they become the new secondary wavefront. Right? If the first wavefront is plane, then the second wavefront will be a plane. If the first wavefront is spherical, then the second wavefront will also be spherical in nature. Right? Now, this Huygens principle is used to locate the position of a new wavefront, the shape of a new wavefront, like that. So this is all about the Huygens principle. Now, let us move on to the reflection of a plane wavefront now. Now I'm going to, so reflection of a plane wavefront, that is, this is a proof for laws of reflection, right, on a reflecting surface. So reflecting surface means the surface can be a mirror, the surface can be a water surface, right? So x, y be the reflecting surface. So there is a light source here which is far away from us, that is which is at infinite distance. Now some light rays, I am going to take two light rays from the light source. They are incident on this reflecting surface. So P A and Q B C. The PA and QBC are the two rays which are incident at the points A and C respectively. Here AB is called as the incident plane wavefront. AB is the incident plane wavefront. So this is the angle of incidence, right? This AB, that is this incident plane wavefront, is perpendicular to the plane of the board, and these rays PA and QBC are also perpendicular to the incident plane wavefront AB. Now I am going to draw a normal at the point A. So I am going to take this as the angle of incidence, right? So according to Heisenberg's principle, each point on this plane wavefront, that is, if I take so many points on this plane wavefront, each point on this wavefront act as a source of secondary wavelets. So whenever there are so many rays in between these two rays, so they form wavelets, right? Now, by the time a wavelet from this point B reaches C, by the time a wavelet from B reaches C, a wavelet from A would have reached a distance which is equal to BC. That is here along this direction. See, by the time a wavelet from B reaches the point C, a wavelet from A would have reached here in this reflected ray. So would have reached a distance which is equal to, that distance is equal to BC. So keeping this distance BC as radius and A as center, I am going to draw an arc. So draw an arc. From the point C, I am going to draw a tangent which touches this arc. Now this is marked as, this point is marked as D. Here CD is called as the reflected plane wavefront, and AD is called as the reflected ray. So AD is the reflected ray, CD is the reflected plane wavefront, right? So now, so since this is the reflected plane wavefront, this is the angle of reflection, right? So here I get two triangles which have a common, that is, which are at 90 degree each. Since they have a common B and D and common AC, that is common base AC for both the triangles, they are said to be the congruent triangles. So ABC and ADC are congruent triangles. So B and D, the angle B and the angle D are same, and AC is common for both the triangles, right? And from this triangle, it is confirmed that the angle of incidence is equal to the angle of reflection, right? Now, so this ray would have been reflected along this direction. So, according to first law of reflection, the incident wavefront, plane wavefront, and the reflected plane wavefront and the normal, so if this is considered to be NA, right? The normal lie on the same plane. So the second law. So from the second law, we are going to derive some equation, right? Now, here the angle PAN and NAB. So PAB is equal to 90 degree. So I can separate this as angle PAN plus angle NAB is equal to 90 degree. Also, angle PAN alone is angle of incidence is also equal to BAC, which is also equal to angle of incidence, right? So also this 90 degree minus NAB, 90 degree minus NAB is also equal to the angle of incidence, which is also equal to BAC. So there is a mnemonics for this. Pan, nab, back. So it ends with N, starts with N. Ends with B, starts with B. So pan, nab, back. So angle of incidence is equal to pan 90 degree minus nab or back. Right? Now, again, for angle of reflection we have to find. Here, N, A, D and D, A, C. They are also 90 degree. Right? So again, angle N, A, D, because it is reflected ray, right? N, A, D plus D, A, C is equal to 90 degree. Again, angle of reflection is nothing but angle NAD, which is also equal to 90 degree minus DAC, which is also equal to DCA. So again mnemonics. NAD 90 degree minus DAG DCA. We can also write CDA like that, no problem. So CDA, but it's better. So DCA, so angle of reflection. So NAD, DAG, DCA, right? So this is the angle of reflection. So we said that this angle B is equal to angle D and AC is common. So these two triangles ABC and ADC are congruent triangles. So it shows that the angle of incidence is equal to angle of reflection. So this is the proof for the loss of reflection or the reflection of a plane wavefront on a reflecting surface. I think you should have understood. So thanks a lot. In the next video, we'll look on to the refraction of a plane wavefront on a plane refracting surface. So thank you, students. Bye.